All right. Hello, everybody. Good morning.
Morning.
Good morning to those in South and Southeast Asia. Good evening, America. I hope you are well, staying safe and healthy. I'm Hesti Wulandari from ITB. I'm pleased to welcome you all to the International Virtual Course on Astrostatistics and Machine Learning. This IVC is organized by ITB and NARIT. I hope you would enjoy and learn many from the lectures as well as from the hands-on activities. Now let us start. Let me invite Professor Wahyu Srikutomo, Dean of the Faculty of Mathematics and Mathematics and Natural Sciences of ITB, to deliver his speech and to officially open this IVC. Professor Srikutomo, please.
Thank you, Bu Hesti. Assalamualaikum warahmatullah. Good morning to you all. My name is Wahyu. I'm the Dean of the Faculty of Mathematics and Natural Sciences of ITB. This morning, I would like to express my sincere gratitude to all of you, the participants of this international virtual course on astrophysics and machine learning. And also, I would like to thank Professor Eric Feigelson. Good morning, Eric. And thank you very much for your participation and willingness to sharing your thoughts on the astrostatistics and machine learning and all the topic related to this major themes. And I would like also to welcome all the participants from Indonesia and all, as well as those from other countries. I hope that this international virtual course will bring us closer to the condition where we can earn optimally from this event. I hope that this virtual course will can be a bridge of bringing together all the scientists from all over the world, or participants from every country participating in this event, and we can share thoughts or ideas, and also make possible scientific communication between or amongst the young researcher, young students, and all the professors involved in this event. And I hope also that we are in the condition of good health always, and I also hope that we can manage to complete or to finish this event as planned. I think that is my simple speech for this morning. Again, I would like to thank the committee, the organizing committee of this event, Bu Hesti and other and other from astronomy of ITB. Pak Hakim, good morning. And
morning.
And by this simple speech, I officially open the virtual course, international virtual course on astrophysics and machine learning. Thank you very much. Assalamualaikum. Good morning to all.
Thank you very much, Professor Wahyu Srikutomo, for opening the IVC. Now let's move to the photo session. I would like to invite you all to open your camera. I think Firda will be helping us in taking the pictures. So give your sweetest and most optimistic smile, please. Firda, are you here?
Yeah, okay. So we are gonna take picture together. Please open your camera. Okay, let's start. 1, 2, 3. Okay, wait. Okay, again. 1, 2, 3. Okay, the last one. There are still many who are not open the camera, so please open your camera. Okay, so just 1, 2, 3. Okay, thank you.
Thank you.
Okay, thank you very much, Firda, for taking our pictures. Now let's proceed to the first session, and I will invite Dr. Iqbal Arifianto to lead the session. Pak Iqbal?
Yes, yeah, thank you, Bu Hesti. Good morning and good evening to everyone, all the participants, and also to Professor Eric Feigelson and to other lecturers here. Before we start the lecture of Eric, I will present some information about this school. Let me share my screen first. Okay, can you see? Yeah, can you all see this screen, right? Yeah. Okay, welcome to the International Virtual Course on Astrostatistics and Machine Learning. This course is open to advanced undergraduates, students, and master students in astrophysics have interest in use of statistics and machine learning to tackle modern astrophysical problems. So the material will be delivered about regression, Bayesian statistics, MCMC, time series analysis, clustering, classification, deep learning, and actually not all scope of astrostatistics was covered because it's limited time, but we really want to present this school to cover some of the topics, and also all the participants will start using the hands-on problem. Okay, there's lectures, tutorial, and hands-on sessions. Yes, and we'll question discussion using Slack channel for this lecture. Okay, I want to share the rules of this course. This IVC is equivalent to a master course with 2 semester credits. All the IVC participation score and certificates will be awarded to participants who attend more than 80% of the sessions and do the tasks and hands-on problem assigned by the lecturers and tutors. By the end of the school, there will be a student presentation sessions. Each group present one of hands-on problem with the new data and analysis. So work with your group. And all lectures and slides will put on the Google Drive link and links. Yeah, I should report to you all that all the participants, number of participants is about 50 participants from mostly in Southeast Asia and Asia, 52% from Indonesia, and the other from Thailand, Singapore, Malaysia, Philippines, Pakistan, Nepal, India, Bangladesh, Taiwan, and one from USA. About 56% from men and 44% women participants. And the degree, about 28% is advanced undergraduates from astronomy and physics major, and about 22 participants from the master students. And the lecturers, it is today we have Professor Eric Feigelson, and so we have also Dr. Tri Laksamana and Dr. Hakim Malasan, Dr. Nurhasliza Yusuf from University of Malaya, Professor Eric Feigelson from Pennsylvania State University, Dr. Tri Astra Atmaja from Space Telescope Science Institute, Dr. Hakim Malasan from Institute Technology Bandung, and Dr. Nurhasliza Yusuf from University of Malaya. And for the machine learning topic, we have Jakramate Bukrajam from Chiang Mai University, Dr. Utan Sawangwit from Narit, Thailand, Dr. Naoto Nishisuka from National Institute of Information and Communication Technology. And so we have Professor Taufik Hidayat from ITB, Professor Bunraksar Sontorntum from Narit, Thailand, and Dr. Anirudh Prikse from Narit, Thailand. And also we have tutors for this, because all the participants will be guided in the tutorial session and hands-on with tutors. We have 8 tutors. For the coordinator tutor is Dr. Anton Jailani. He's a PhD in astrophysics. Now he's a lecturer in the astronomy department, astronomy research groups. Also we have Sulistiawati. Current post, she is in HR data analyst in Influx. She's a research assistant. Now we have Isnainda Iksan. He is a lecturer in atmospheric planetary science study program in ITERA. He's also a PhD student in astronomy. We have also Dr. Ibnu Nurul Huda. He is a postdoctoral in astronomy research group in ITB. Now we have Rizky Muhammad Nur Hidayat. Now he's in writer on the startup and toward data science. We have also Salma Zahra Fadia. She's a master student in astronomy. And the last one is Irfan Imaduddin. He's a master student in astronomy and also research assistant, astronomy research group, and also in Boscha Observatory. Okay, that's all from me. We'll start the lecture. I will stop the share screen. And yeah, today we have a lecture from Dr. Professor Eric Feigelson. He's astronomy from graduate from Harvard University. Now he's a lecturer and professor in Penn State University. He's also inaugural president of International Astronomical Union Commission on Astroinformatics and Astrostatistics. He's also a statistical scientific editor of American Astronomical Society journal. And his research area is in X-ray astronomy, astrostatistics, focusing on statistical approach to exoplanet detection based on parametric autoregressive modeling. Okay, that's all I don't want to talk much. Okay, please, Eric.
Okay, can you hear me?
Yes, yes.
And now I'm going to share my screen.
Yes, please. Okay. Eric, for question session, do you want to in between the lecture or after, in the 50 minutes after the lecture?
I think we can interrupt me
Okay.
during the lecture. So
Okay.
if
Yes, please, participant raise hand. So I will show you and to speak to directly. Thank you.
So I do not have too many slides.
Yes.
I am not trying to cover a vast amount of material. So we have time to get to know each other a bit and to discuss things, either what I'm saying directly or even around it, things that interest you. You are now seeing my screen?
Not yet.
Yeah. No, hold on. Not yet. That's right. I pressed the wrong button. Okay, now you are seeing my screen,
Yes.
I think.
Okay.
Yeah, good. There we go. Okay, so first, I'm very pleased to be here. I'm an American astronomer, and I've never been to Indonesia. I've never been to Bandung, but I did go to Chiang Mai, Thailand 2 years ago, where I met a few of you, and that I think formed a little connection between me and Southeast Asian astronomy in this particular way. You've already introduced me so nicely, so I won't go into this, but I think the essence of it is that I'm just an astronomer, a research astronomer, and I teach, but I happened to walk into the statistics department to ask a question more than 30 years ago when I was an assistant professor. And I couldn't believe the answer. The answer was, your question is an entire field of statistics that had more or less been invented in the second half of the 20th century, a fairly new field. And then it answered all my questions and many more methods, which I didn't even know the question of. It happened to be called survival analysis. And it was a method, these are a field for dealing with what they call censored data and what we call upper limits. When you take a telescope, when you look at 100 objects, you only see 70 of them, 30, you have little arrows pointed down. They have statistical methods for dealing with this based on theorems. Famous methods, very widely used in industry, in biomedicine, but the methods were unknown to astronomers. So this experience that I walked in to the office, this consulting center of the statisticians when I was young, I have never left. Since then, I have been friends with them. I have talked to them. I listen to them. I sometimes go to their conferences. I try to engage them in astronomy, and there's two ways of engagement. First, I and we on our side, we read what they do, so we learn what they know. And they know an enormous amount. And then the other direction is we have problems that are very difficult or tricky or unusual. And we try to engage the statistician to help us to do new theorems, to develop new methods with us for our problems. That part has not gone very far. It's not many statisticians, only a few, who really work with astronomers seriously. But in the other direction, the learning part, this is now progressive. And we at Penn State, I'm a large university in America, public university. We sort of have specialized in this, which is we run summer schools very much like what you're attending right now. And we run them in person, and now we're running them virtually just like you are, because everyone must stay at home because of COVID-19. We also run conferences called Statistical Challenges in Modern Astronomy. The last one was just a few weeks ago. Oh, that should be 2021. Whoops. Anyways, so we've been running them for 30 years. My goodness, 30 years of conferences every 5 years, mostly at Penn State. And that brings in statisticians and advanced astronomers to talk about the difficult challenges. We also wrote a textbook that came from the summer school. And the textbook is for astronomy graduate students or master's students to learn sort of 20th century astronomy statistics, sort of older statistics. It's not the latest in machine learning, not the most advanced neural networks, but the foundations of statistics that are useful to astronomers, or at least we think they are. And then I've done some organizing. I've this business of the IAU. I helped organize to get astronomers to be more active in this area. And I'm now an editor of journals where I don't read the articles for astronomy and astrophysics. I read them for just the method section. And I try to help if they have problems as an editor for the American Astrophysical Journal and Astronomical Journal. Just what I've done. Here's our textbook. Modern Statistical Methods for Astronomy. Then it says with R applications. And actually, I'm going to talk to you a little bit about R. When we teach it at Penn State, we teach R, we teach you the language. It's a computer language that is designed, written by statisticians. And it includes much, much more of modern statistics. It includes almost all of modern statistics. And it grows rapidly. And therefore, it's useful as a toolbox that is bigger than Python's toolbox, maybe even better in some ways, depends on the issue, than Python. And therefore, students, astronomers, researchers who are interested in statistical methods of doing the more advanced things, they often have two languages, Python for general astronomy use and R for advanced statistical use. So I'll show you some slides at the end today about R. And that's the last you will hear about R, I think, well, a little bit, but not much. I'm not going to teach the language here because there's no time. And so that's who I am. I'm Eric, and you should feel free to talk to me by Slack or by email over the next 4 days. I will see you 4 times, so we get to know each other a little bit. I wish we were together, but this is the way things are. Okay, so what am I going to talk to you with this introduction? You'll find that, again, I do not generally talk about the most modern, the most advanced, and the most computational aspects. I tend to talk about foundational concepts and the methods that emerge from these foundation concepts. So in a sense, from me, you get sort of a background. And from other lecturers, you will get more modern methods and more practical, perhaps. But foundations are important. So we're going to start off with what might almost be called philosophy. What is the role of statistical methods for astronomy? And then very briefly, some history of the interactions of the two perspectives. Then bring you up to date to what is going on in terms of the field, but no details yet. This is just introduction. So you're not going to learn anything useful today from me this morning, only general historical things. But I do have a purpose. In some ways, I want to not change your mind, but sort of broaden a new perspective on astronomy that most physicists, we're trained in astrophysics. We don't have this perspective. and then perspective can be useful in our work. Okay, so let us start then and talk about astrostatistics. And I thought that in order to say what is astrostatistics, I should first say what is astronomy and then what is statistics. So what is astronomy? Well, actually, for the last half century at least, astronomy is really two things. It's astronomy and astrophysics. Astronomy is the observational study of matter beyond Earth, the planets in our solar system, the stars and their planets in the Milky Way, recently discovered, the other galaxies beyond the Milky Way galaxy, and also there's a lot of material between stars and between galaxies that is not yet collected into gravitationally condensed objects. So this is telescopes, radio telescopes, optical telescope, infrared, X-ray, gamma ray. Some are in outer space, some are on a mountaintop. Occasionally, they don't even have photons. They are in the underground or under the ice or something. Astrophysics tries to seek understanding of the intrinsic physical nature of these astronomical bodies. What are they made out of? What is their temperature? What is their mass? And then physical processes, the gravitational processes, the radiation processes, and maybe their evolution. How were they formed? How long will they live, and how will they die, in a sense? So this is this is not at a telescope. This is done in an office with your mind, with a blackboard, with a library, maybe a computer for computation of equations. So it's this is an intellectual effort to understand the astronomical phenomenon. And we're very lucky because the laws we've discovered on Earth that refer to terrestrial phenomena seem to work perfectly out there. The Lyman alpha line from a quasar is the same Lyman alpha line from hydrogen in a laboratory today. So because of this powerful connection between physics on Earth and the celestial bodies, we can understand a lot. And that's really our goal. First, to look and understand, characterize and discover and characterize, and then to understand. What I'd like to say is that nobody debates this. Everyone agrees what astronomy and astrophysics is about. So if you go ask about a statistician, what's statistics? They don't agree. It's rather surprising. Okay, now they had one very great figure in the 20th century. He started as an undergraduate in 1916 to revolutionize statistics. His name was R.A. Fisher. He lived in England. And in one of his very first book, he says briefly, and its most concrete form, the object of statistical methods is to reduce your data. Now we understand that, you and me, because if we go to a telescope and we take 100 CCD images, we have gigabytes of information, terabytes. The whole field has petabytes of information. We have to reduce it down because the human mind cannot understand gigabytes and terabytes. The human mind understands a table with a few lines and a few columns, a few kilobits of information, and a graph with a curve or a few curves or a histogram or something. We basically can only understand kilobytes. So we have to go from terabytes to kilobytes. We reduce the data. And quite frankly, astronomers are good at that. We know how to write pipelines to analyze our CCD data, our radio interferometry data, our Poisson processes from a gamma ray telescope. We're pretty good at this. Not perfect maybe in methods, but we know what we're doing. We built the instruments. We should know. Now, more recently, if you go to Wikipedia, which by the way is excellent in statistics, it says a few years ago, statistics is the mathematical body of science that pertains to the collection, analysis, that's more or less what R.A. Fisher was talking about, but also the interpretation or explanation, and also presentation, graphical visualizations, things like that, of data. The important thing is that statistics and statisticians do want to help you understand what's going on. And from our perspective, they want to help us do astrophysics from our astronomy data. Just to show that they don't know what they're talking about, they changed the wording of this in 1 year, just a few years ago. I don't know why. Now, here's another famous statistician, David Cox, again from England. This is one of his first books. He's still alive. He's like 98 years old, I think, in England. This is not all of statistics, but it's an interesting part of it. A statistical inference carries us from observations to conclusions about the populations sampled. Now, he's probably thinking of human populations, and they do an experiment with 500 humans, and they try to infer something about humans in general. But for us, it's stars or galaxies. I would claim that when you do your master's thesis or dissertation, you're not interested in your 200 Seyfert galaxies. You're not really interested in them. You have data for them. You're really interested in Seyfert galaxies in general. And you want to understand the accretion processes onto supermassive black holes that power a Seyfert and why guys that have these characteristics. So you want to go from 200 objects where you have some information about them to understanding the underlying population and the processes underlying. So I think D.R. Cox's comment is relevant not to all of astronomy, but to some of it, a good portion of it. So now, does statistics help scientists? Right? It could be used by other groups of people. It could be used by, I don't know, politicians. Could be used by other purposes, by industries. But does it help does it help scientists? And actually, very strangely, in my opinion, the most prominent statisticians of the 20th century are very negative about this. They're pessimists, in my opinion. The famous quote by George Box, who was the son-in-law of R.A. Fisher, essentially, all models are wrong, but some are useful. All models are wrong? I don't think Box meant an astronomer who studies binary stars, because we understand Newtonian gravity and Kepler's orbits, and our models are not wrong. They may be wrong a little bit. There may be a third star or some distortion, but fundamentally, we understand some of our situations very well. But he spent his life talking to social scientists, businesses, not to astrophysicists who understand things. So that's why he was a pessimist, in my opinion. Same with C.R. Rao, also 100 years old. He now lives in India. He was R.A. Fisher's last student in the 1940s. And he quoted a very famous historical piece of astronomy. I don't know if you know this about the history of astronomy, but when Copernicus wrote that the sun was the middle of the universe, center of the universe, not the earth, it was very controversial. The Catholic Church didn't like this. So his uncle, who was a bishop of the church, put a preface into the book and said, oh, there's no need for these hypotheses to be true, the hypothesis of the sun in the middle, or even to be anything like the truth. It should just yield calculations which agree with the data. So I don't know about you, but I don't feel that's our goal in astronomy and astrophysics, to just find some arbitrary model that agrees with the data. I mean, sometimes that's useful, but we really want to understand things. And D.R. Cox wrote in his last book, and I'm not going to read the whole thing, but basically he says that the use, if any, of quantitative notions of probability for scientific inference is unclear. Again, he's a pessimist. Now, I will now give you a more positive view. This individual is not so famous. His name is Phil Gregory. He's a retired Canadian radio astronomer, and he was one of the first in his generation to wake up to the potential of Bayesian inference for helping astronomy to astrophysics. And let me quote from his preface of his book. The first sentence here is commonly said. Okay, this is sort of standard scientific method. The goal of science is to unlock nature's secrets. Our understanding comes through the development of theoretical models, which are capable of explaining the existing observations and making testable predictions that we can go to the telescope and test whether it's a good theory. The second sentence is more relevant for us. Fortunately, a variety of sophisticated mathematical and computational approaches have been developed to help us through the interface from astronomy to astrophysics. And these go under the heading of statistical inference. The math of modeling, taking Kepler's laws and finding the eccentricity of the binary star, the mathematics of that process is called statistics. Now, I told you I've been talking to these guys for 35 years, okay? So let me try to summarize in one slide. This is my most important slide in all the 6 hours you're going to hear me. This is the most important slide. What do I think astronomers should do with statistics, okay? And what good is statistics? Well, I am more on the side of Phil Gregory. I am a positivist. Most astronomers, I think, are. So I would say the application of statistics can reliably quantify information that it is embedded in your data. And then, okay, now I'm going to listen a little to the skeptics. Instead of decide what the theoretical model is, I'll say it might help adjudicate, help judge the relevance of theoretical models. Because maybe our theory is wrong. And maybe we can use statistics to eventually show it's wrong with better data. Or maybe we'll validate it and show a more elaborate theory is needed, more details, maybe more different abundances of the elements or different temperatures or velocities, and may not be so simple as a simple theory. So but statistics is good. I don't believe it's useless. Okay. But the thing that I've learned from the statisticians is that it's not simple. It's not a straightforward mechanical enterprise. I think a lot of astronomers view statistics as, no, I'm sorry, you're from Southeast Asia. I don't know if this is a good analogy. But in America, we would say, you have two pieces of wood, and you want to connect them, and you get a hammer, and you go bang, 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 and you just hammer it together with a hammer and a nail. It's mechanical. There's nothing to think about. You just do it. So that, I think, was the error of my generation and older generations of astronomers to think that it was easy. And here are the steps that I see, and the ones at the beginning particularly, astronomers of my generation, maybe yours too, I don't know. We're not spending enough time and energy at. First, explore your data. R.A. Fisher also said, we think he said, let the data speak for themselves. Now, we know you may have a theory involved with your Seyfert galaxies or your binary stars, but take a look at the data and use statistics to just characterize it without any models, called non-parametric, exploratory data analysis. You might find the data is no good. You may find the data has noise in it or something that you don't want or expect. You might see some features that are new and discover something. So explore the data non-parametrically. Then state a problem. And from that problem, formulate a model in mathematical form. It could be the model of an ellipse. Could be the model of MHD turbulence. By the way, from the same data, you're not restricted to only ask one scientific question. Today, you can ask one question. Tomorrow, you can ask another question with another model for a different purpose or a different exploration. Then you choose statistical methods. And I and the other teachers in your workshop here will be teaching you some methodology. And that's actually rather confusing because there's a lot of it. Then you actually do the calculation, which means you write a code and you run the code on a computer. Now, what I want to say is that this is actually the easiest part. With Python, which by the way is very good at machine learning, it's not so good at some other areas of inference. With Python and with R, you basically don't have to write any statistical program ever in your life, your career. You just have to use them. The hard part is knowing which ones to use and how to use it. But then you don't have to write much code. And then think of D.R. Cox and C.R. Rao and George Box. They were skeptical. You got to judge, step back from the methods, step back from the calculation, and judge what's the meaning of that result with respect to my scientific question that I asked up here. So what I would say is here you explore, and you think, think, think. Then you write a little code, and then you think. Much more thinking than just hammer, 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 hammer. I did it. That's what I recommend. Slow down and think and learn. You're learning statistics you don't know. Okay, now this slide is just more comments of things that I sort of feel after speaking to the statisticians, okay? Sort of just talking about this a little more disorganized. Modern statistics, it ends up, is huge. I think it's the size of physics. It's bigger than astronomy. It has more journals, more books. It's just amazingly deep. And it's very hard to find things. They have terrible jargon. Words mean different things to them. The word linear doesn't mean what we think linear means. They have abbreviations like IID. I mean, just crazy stuff. And then when you sit down with a statistician and tell them your problem and what your goal is right today, they may give you 5 different ways of doing it, including 2 completely different conceptual approaches, and then variations within them. Frankly, statistics is very confusing, and they have not found a way of communicating, more than trivial. Elementary statistics is easy, but advanced statistics is not. In my personal opinion, by the way, It's not that hard for us, for you and me. If you have taken courses in electromagnetism and quantum mechanics, you are smart enough to learn almost any statistics. It's not that hard, the math. The math is harder than physics. That's my opinion. Okay, now here's another point. Some statistical procedures are based on mathematical proofs, theorems. And the theorems say for these assumptions or axioms or whatever, then you get this result by mathematical theorem proof. And that is absolutely true, like 2 + 2 is 4. It's true. And you should never violate a theorem with knowingly. Okay, it's like saying 2 + 2 is 6. It's not true. Now there's a problem. Some issues don't have proofs. Sometimes there are 2 proofs in 2 different areas with 2 different concepts behind the proof, and they can't decide which one is right, like in model selection. And there's even at least one proof, which is fascinating. Go to Wikipedia, type in the no free lunch theorem. It's a proof. There is no proof for deciding which of machine learning methods are useful in classification, which is a major branch of machine learning. There's a proof that you don't know what you're doing. You cannot decide what to do. It's a very bad proof. I mean, it's a very dangerous situation. But there are other times when the proofs are very powerful, like maximum likelihood estimation, all based on theorems written by R.A. Fisher and his students. Now, I'm an editor of a journal, and my job is to help the editor, other editors, make sure that the articles published in our journals are good, reliable articles. They have good observations and good calculations and good scientific inferences, good astrophysical inferences. We don't want the science result at the conclusion to depend on sort of some of these arbitrary choices being made in the methodology, or choices of scale, like whether you use kilometers per second or parsecs per year. We don't want the method to depend on stupid things like units. Many methods do depend on units. And many results will differ with different methods applied to the same problem. How do you know what's right? I don't know. Sometimes you can't know. Sometimes you struggle to understand the differences. Sometimes you find that the results flop around, science results flop around with different methods. Maybe you shouldn't publish. Maybe you don't have enough data to get a reliable result. Or maybe you can do non-parametric work where there's no parameters. You just ask hypothesis questions, or certain scale invariant methods. Some methods don't depend on units. Generally, my suggestion is go ahead and do what you think is your way of doing it, then go back after you're finished and try another method or two and see if you get the same answer more or less. Then you can feel better, more reliable. By the way, this is easy to do in R. That's a little harder in Python, more lines of code, but it's very possible in Python too. And then Dr. Cox. Is statistical results useful for science? Well, be cautious. Don't assume that because you have 3 sigma, that the answer is yes. It could be your 3 sigma for some other reason that's not scientifically interesting. Like there's a selection effect, or the sample is so large that everything is significant. Okay. Remember, statistics is just a tool. You and I are not statisticians. You and I are astronomers and astrophysicists. So it's a tool. It's a huge toolbox of tools, a big box of many tools. So we should increase our knowledge of statistics, and that's why you are here for 1 week. and be thoughtful and maybe even cautious about the interpretation of the result. Does anyone want to say anything now that I finished my philosophy?
Yes, if there's any questions from the participants or
Yeah, hello Iqbal.
okay.
Eric,
Yes.
can you hear me?
Yeah, Pak Hakim.
Yes, I can hear
Yes,
you.
yes, Eric.
clear.
I'm one of the lecturers, so I'm not a student, but it's very interesting to hear your philosophy about the statistics. Well, in the first problem in astrophysics, I think there some has no major theory yet or concept that should explain the underlying principle of what phenomena that we observe. So in that case, to what extent can we rely on statistics?
Okay.
Could the statistics drive the theory, the concept for that?
This is the situation of the biologist and the social scientist. There's no theory of society, of humanity, of psychology. They don't understand anything. So the answer is that mostly they do simple, do you know the word heuristic models? Heuristic or ad hoc. You just make up the model without pretending that it means anything. And usually they make up and we make up a linear model and hope it fits and hope we try to learn something from the slope or the intercept of a line. We do very simple things the same way the social scientist does. And so Hakeem, I don't think it's hopeless. In fact, if so, all quantitative social science is hopeless, but it's certainly not as, it's not as powerful as having Kepler's orbits for a binary star.
That's right.
Okay, I'm going to go a little faster. Oh, I have to press another button. There we go. Okay. Okay, let's do a little bit of history. So it ends up that statisticians love astronomy. They think astronomy is wonderful, but they think of astronomy as wonderful only before about 1850. Okay, so let's go to the, and you are Asian, so you do not have a Western history, you have your own history. But in the European world, we think back to the ancient Greeks and the Romans and the Middle Ages and the Renaissance, and then the Age of Enlightenment. And this is Western history. So let's take the, how did the ancients estimate the length of a year? So Hipparchus did this in ancient Greece, 2,500 years ago. And he made a bunch of measurements, and I'll just make them up. He got 264 days, 267 days. No, sorry. 364 days, 367, 365, and 382. He made several measurements. And the answer, of course, is 365 days in a year. And he didn't know what to do. So he took the maximum and the minimum, and he took the average of those two numbers right in the middle, even though there was no measurement there, the middle of the range. And that's very intelligent. But nobody does that anymore because it's very sensitive to mistakes. One bad point, too high and too low, then the whole middle moves. And it's not what is called robust. Not robust to non-Gaussianity. In medieval times, when the Catholic Church was dominant in Europe, the theologians interested in science said, observe once and stop. And you know the answer. If you keep on observing, you keep on getting these different numbers and you lose knowledge, not gain knowledge. This is very amusing because this is exactly wrong. But it's consistent with their theology. So what we now think is you should add up all the numbers and divide by n, and that's called the mean. And that was first done prominently by Tycho Brahe in the 1500s, the great astronomer. It was done also by Galileo in the next generation. This was the Renaissance of science. And astronomy was the great field of science. But if you go and ask 10 statisticians today in 2021, how would you estimate the length of a year? They might say, well, the mean is okay, but even the mean is sensitive to a bad number, especially the standard deviation is, and they would recommend the median, the middle value. It's the most stable of them. It's robust to outliers and non-Gaussianity. And then you might say, but I want to get the standard deviation too. Well, they said, well, okay, you've got two choices. There's the MAD, the median absolute deviation. It's a non-parametric estimate of spread, like the median is a non-parametric estimate of location. Or a method devised in the 1980s called the bootstrap. And you need a computer for this. Bootstrap resampling to get the uncertainty of the median. That's what they probably recommend today. So I just want to give you an example how it's been 2,500 years of astrostatistics, and we're still debating the question, the answer. Even something as simple as that. Now, the big discovery was in the beginning of the 19th century, in 1800 and 1820. These three scholars, Adrien Legendre, Pierre-Simon Laplace, and Carl Friedrich Gauss, France and Germany. They developed simultaneously and together with competing theorems, they were very competitive, least squares regression and the Gaussian distribution called the normal error theory. And for many decades, astronomers were the leading statisticians in Europe, contributing to least square theory. By the way, you may know of Gauss from magnetism. You may know of Gauss from mathematics. He's a physicist, a mathematician. Do you know what Gauss's job was? All of his adult life, he was the director of an observatory. He was doing budgets for astronomers or something, who knows? A very great man, I'm sure. Okay, so what happened after the 1800s? And the answer is rather sad. In the late 1800s and early 1900s, statistics moved away from astronomy and moved into the human sciences. Demography, economics, psychology, medicine, politics, and industrial applications, agriculture, mining, manufacturing. A very effective R.A. Fisher worked for Her Majesty's Agricultural Service. And we moved away from statistics also for other reasons. We had already discovered Newtonian gravity. That's what they needed this for. This was celestial mechanics. But now we discovered, or rather the physicists discovered, and we quickly adopted electromagnetism, thermodynamics, quantum mechanics, relativity. All of modern physics sort of got absorbed quickly into astronomy, and we became astrophysicists by the middle of the 20th century. The big success was stars, understanding stars. And now understanding the universe with general relativity. So astronomers and statisticians essentially broke contact. The curriculum of astronomers was based on physics, but not statistics anymore. And the statisticians also lost track of us. And they don't know a quasar from a pulsar. They don't know anything. They just don't know anything. They don't follow us. So when I came around the last part of the 20th century and the beginning part of the 21st, Astrostatistics was pretty weak when I was young, but now it's improving. Still, many astronomers just use a narrow suite of very familiar methods. If it's a light curve, they only do Fourier analysis. They just don't learn anything else. That's old. They still use least squares regression, which is not necessarily wrong, but it's old. It's not as powerful as other things. For instance, Pearson's least chi-squared method is still used by astronomers. It's not. It's often not a good idea. We still use the Kolmogorov-Smirnov goodness of fit or two sample tests. It's based on a theorem. It's not wrong, but there are better ones. The Anderson-Darling test is better. We don't know that much about what to do with many variables. Let's say we measure 10 properties of the galaxies. We should use multivariate statistics. And except for PCA, we don't really know much multivariate methods. And even when we have traditional methods, there are errors that we make because we just don't take the courses. We don't have the background of modern statistics. And here, these three problems here are in these three papers here. And so that's why we wrote the textbook, essentially. And that's really what I'm going to do with you and what we do in our summer school, is we try to catch up young astronomers with 20th century methodology. For instance, in modeling, we teach you maximum likelihood estimation. That was brilliantly created by R.A. Fisher. In 1977, the EM algorithm is used to maximize the likelihoods with the theorem of convergence that MCMC does not have. That paper has, I think, 60,000 citations. It's one of the most famous papers in mathematics of the 20th century, how to maximize likelihoods. Then there's the Bayesian information criterion and other model selections, and the bootstrap, wonderful method from the 1980s. Then there is the wonderful world. You will be learning this from your other instructors, not from me. Classification. R.A. Fisher, a primitive one. Linear discriminant analysis. It assumes multivariate Gaussian distributions, which is usually not true. A more sophisticated one from a Russian mathematician named Vapnik. Support vector machines. Powerful theorems underneath. A very practical one, no theorems, by Leo Bryman, an American statistician, called Classification and Regression Trees. And from that, he developed random forests before he passed away about 20 years ago. In time series analysis, most of the world uses autoregressive models, but not astronomers. And we can do more sophisticated modeling with state space representations. For spatial point processes, astronomers use only one method consistently, the 2-point correlation function and the friends of friends algorithm. Both of these are of limited use. There's an enormous field on how to analyze low dimensions, 2 and 3 dimensions, sort of clustered or grouped points or structured points. Huge field, wonderful field that astronomers don't know. This is the one that I found by accident. When we have non-detections, we know it's fainter than, so many ergs or Janskys or something. You can use survival analysis. It's not perfect, but it's certainly better than the other methods we were trying to do. In image analysis, astronomers are not reading enough of the computer vision literature. And this is the huge field of engineering for analyzing images. We also don't know enough about multiple hypothesis testing. This is another paper written in 1995 by 2 Israeli statisticians with, I don't know, 20 or 30,000 citations. We should know these things. It's relevant for source detection and many other problems in astronomy. And then we simply don't know the language R, which is not a very difficult language. It's just the same as MATLAB or IDL and not too dissimilar from Python. The only reason to know it is that it has many more methods from modern statistics. So my last slide, I think is the last one of this sort of category, is sort of to say, you know, I don't think astronomers are sort of stupid. Okay, it's not as though the reason we're not doing modern statistics is because we're just lazy. I think the reason we're not doing modern statistics historically, we're just beginning now, is it is very difficult. And the reason it's difficult is illustrated in this slide, which I'm not going to read. Here I've chosen a very important field of astronomy and astrophysics, cosmology. And here I wrote down, I don't know, a dozen problems in cosmology. Some of them are very big. Weak lensing is just huge. Okay. The lambda CDM is the consensus model of the universe. There's billions of euros being spent on these questions. Okay. And this is my attempt, excuse me, to say, what would a statistician call the problem? And it ends up that you need a lot of different methods in statistics just for cosmology. It's not just one thing, which in social science, it tends to be just pretty easy. You learn multivariate statistics, a little bit of sampling theory, bingo. You could become a PhD in sociology, quantitative sociology. Couple more courses, you can be a biometrician. But in astronomy, you actually have to know almost all of graduate level statistics to do a good job. And that's why it's so hard. And that's why I can spend 30 years at this, because it's actually hard. It's not simple at all to do a good job on every branch of astronomy and for all of the problems that you will encounter in your career. So now I have a couple slides on the present day, 21st century. And I will say things are rapidly improving. Okay. So in the journals that I'm involved in, astronomical and astrophysical journal, a couple others, there's 1,000 paper log number of papers per year. 3 is 1,000. There's 1,000 papers a year on classification. There's 1,000 papers a year doing regressions. There used to be only tens of papers doing Bayesian regressions or in parameter estimation using Bayesian inference, but now most of them are Bayesians. Rapid growth, exponential growth. This is linear time, log papers, exponential. The doubling time scale is maybe about 6 or 8 years for Bayesian. Then there's a popular smoothing operation called Gaussian processes regression. It was very low, and it's been growing exponentially. Machine learning has been growing exponentially, time scale of maybe 2 or 3 years. And one particular topic in machine learning called deep learning, it's more than doubling every year. And it only began in 2017. Of course, it was only invented in 2011 by the computer scientists. So it's very new, but absolutely important and exciting in solving problems that were too difficult to solve, even with random forest, which is now, what, 50, 80 papers a year, random forest. I happen to use random forest in my research. So random forest is 20 years old. Deep learning is more or less 5 years old. Gaussian processes is a little more difficult. It actually dates back to the 1950s, but it had different names at different times. And Bayesian only began in the 1990s. The ideas of Bayesian go back to Laplace, 1800. But you couldn't calculate anything interesting till the 1990s. So a significant fraction of papers in astronomy now use modern methodology, and in some areas it's growing exponentially, which is pretty amazing. So it's a resurgence of methodology. And then there are training courses. We at Penn State have personally given training courses in Penn State, in India, Brazil, Greece, Italy, blah, 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 blah. And there you are. I just added you there, Indonesia. And Thailand was my last one before. There are research collaborations where professors of statistics work with professors of astronomy and astrophysics at Harvard, Carnegie Mellon, Penn State, France, and Stanford, Imperial College London, Swinburne is in Australia. My personal opinion, this is not a long list. There are only a handful of official collaborations, not enough. There are conferences. We've been giving this conference for 30 years. Jean-Luc Starck at Saclay has been organizing one in Europe for many years. There's an organization in North Carolina that brings together astronomers and statisticians several times. That's now been closed, that organization. And at Caltech, they've been organizing workshops and conferences on astroinformatics, emphasizing computation for almost a decade now. And then the scholarly societies. You've heard of some of them. You've heard of the IAU, International Astronomical Union. They have a commission on this. The American Astronomical Society has a working group. But you may not have heard of the International Statistical Institute. They have a special interest group. There's an independent society called the International Astrostatistical Association, which you can join immediately. The IAA. It's the website is in Italy. The new president is in Cambridge, Massachusetts, United States. The American Statistical Association has one. The LSST Big Telescope has a collaboration. And the IEEE engineers, the largest society, scholarly society in the world, are the engineers. They have a task force as well. Now, all of this in the last 10 years, roughly. And along with astrostatistics, recently, astroinformatics has come. And this is when you have massive data streams and massive databases, terabytes to petabytes, where everything is computationally intensive. You can't even look at the data, it's too much, so you have to mine the data. This is where multivariate regression classification, machine learning is very important, because you cannot do anything without it. But you can't use any machine learning method, any statistical method, you have to use computationally efficient ones, like n log n algorithms, or even something called sublinear, less than n algorithms. Those are cute. There's not many of them. This is where the computation is done on parallel processors, giant supercomputers, or in the cloud. Or we're not using CPUs, but GPUs, which are faster, but not quite as intelligent. And you have to pay a lot of attention to your database management and how to spread the data around. It's a whole series of problems. It is not the same as astrostatistics, but they're like sisters. Astroinformatics, okay, I'll give you a joke, not a joke, a little poem. The statistician helps the astronomer on what to calculate. And when it's a very big data set, the computer scientist helps the astronomer how to calculate. What to do? Astrostatistics. How to do it? Astroinformatics. Now, that's not really true. They're really together. They're sisters. Okay. So a few more comments, sort of more about the modern times, not about the past times. This is my own personal opinion. Astronomers often confuse writing software with the methodology that's implemented in the software. The statistics guides the data reduction, the science analysis and interpretation. Statistics underlies it all. But the software implements it with algorithms and code. You need to do both, statistics and informatics. But statistics is more intellectual, less practical. It's not bang, 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 the hammer. It's more, what should I do with these 2 pieces of wood? Oh, maybe I should attach them there. How should I do that? Maybe I'll get a nail and a good hammer and a bang, bang, bang. And you got to think about it. That's the statistical part. And examples of this is that astronomers, young ones mostly, spend a lot of time talking about MCMC and Bayesian inference, but they don't think as much about formulating the likelihood, the model, and choosing the sensitivity of the priors. Okay, and sometimes they waste a lot of computer time doing fancy MCMC when they don't even have to. They can use INLA, or maybe if it's uniform priors, just use MLE and the EM algorithm. They're not thinking enough. They just compute. Okay, that's because I'm an old guy. I don't compute as much as some of you do, or whatever. So, but on the other hand, machine learning is wonderfully powerful, but only for certain problems. So particularly machine learning is really good at classifying images, deep learning especially. It's just amazingly good at it. So what astronomers have done is they've translated other problems into classification problems for images, like gravitational waves. To find the wave event, maybe you can convert it to an image problem and then run a deep learning method. And that's an example of the clever ways that astronomers are using the new methods to solve many kinds of problems. Another good thing is that there are now textbooks. Okay, here's our textbook that I showed you before. Whoops. But there's 2 older ones. One was Phil Gregory on Bayesian, and one is 2nd edition Wall and Jenkins. They're from Great Britain, I think, or Canada. I don't know. Great Britain. And but neither of them have code. Oh, no, this one has Mathematica code. That's not as common a language as R or Python. And the other textbook you must know about is the one from University of Washington with Jelko Ivichik, Andy Connolly, Jake Vanderplas, and Alexander Gray, who's a computer scientist. They wrote a book on a practical guide of big data with machine learning in Python. And they're writing a 2nd edition right now. But you should also know, maybe I'll show you it in the next lecture or so, or something like this, some of the textbooks written by statisticians for you to teach practitioners, psychologists and chemists and earth scientists and astronomers and biologists, to teach them fields of statistics that are not so well known. And all these books have R in them. That's because it's their language. A new volume with R is published every week for the last 10 years. Could you believe that? It's amazing. So there's a lot you can learn from, and we will learn some of it together in the next few. So my conclusion, except for talking briefly about R, is that there's just no question that since I got involved in the 1980s and 90s to today in the 2020s, there's been tremendous progress, but it's not really finished in a sense. So I think the astronomy graduate curriculum should have a year of statistics and computation methodology. Some of the astronomers should get a PhD in astronomy and a master's in statistics and computer science. That we need more funding to bring statisticians to be funded together with astronomy together to push the frontiers of methodology. This is not well funded at the moment, nowhere. It's not funded anywhere well. that we should use more of R, which is free. R costs nothing. So that doesn't cost any money. Anybody can do it. And we should have more meetings every 2 years, maybe, instead of every 5 years. So that was the second of the 3 items. The third item is short. Are there any comments or questions about my sort of historical and conceptual view of the role of statistics in astronomy? A little more practical than the generalities of the beginning.
Okay, please, if anyone has a question, raise your hand. Okay, from IVC Cedra, please.
Okay, hello, Professor Eric. My name is Chandra, and I would like to thank you for this wonderful lecture. I have 2 questions. First, what does it mean explore the data non-parametrically? And the second is, why do we have multiple methods for one problem, say for classification or for time series analysis? Why there's no one best method for one problem? That's all. Thank you.
Okay, those are 2 questions. Thank you, Chandra. Non-parametrics is a well-defined field of statistics, and it's in chapters 4 and 5 of the textbook. Okay, so unfortunately, I don't have enough time to teach it directly, so I'm not sure I'll be doing much, but I'll try to point it out when I do something non-parametrically in the next 3 days. Often, not always, often non-parametrics don't use the actual numbers, but maybe just sort them like 1st, 2nd, 3rd, 4th, 5th, and they just rank them, and they do calculations on the ranks. So that's an idea where you can't get the mean out of that, but you can still ask questions. And a lot of the time, the questions that are asked are yes, no questions. No parameter is being estimated numerically. But you say, is this sample the same, consistent with this, consistent with coming from the same parent distribution? Yes or no? What's the probability that they come from the same distribution? That's called an hypothesis test.
So it's same like classification. Is it like?
Well, tests tend to have what are called p-values, probabilities. What's the probability that your question is true, or the null hypothesis is true of the question you ask? And so there are not that many methods in non-parametrics. There's only a few theorems. And so there are only a small number of good probabilities out of non-parametrics. But when you do have that opportunity to ask a question, and you can even combine it with parametric modeling, then it's often very useful to do it, because it doesn't depend on Gaussian distributions, on linearity, on the validity of your model. There's no likelihood. It's very always true. The most famous example for astronomers is the Kolmogorov-Smirnov test, KS test. It says, what's the chance that these 2 distributions are the same, one variable? And that's an example of non-parametrics. Now, in classification, when you say there are different ways and clustering, different ways of doing things, why can't they decide on one good way? And the real answer to that, I think, Chandra, is you have not defined the problem well enough. You have not asked a very, very, very specific problem. If you ask a very, then there's one answer to the one problem. But we say, look, just tell us something, tell us what's going on. And they can say, well, we can make these assumptions and take this approach, and then we'll tell you something. We can take these assumptions and that approach and learn something else. And so there's 2 methods, because you asked a vague question. But most science questions are vague. So we are often in that situation where there's multiple procedures and there may not be a method for deciding between them.
Okay, thank you for the answer, sir.
Okay, thank you, Chandra. Next, Arifin, please.
Okay, I hope I'm audible.
Yes, I can hear
Yes.
you. Hello.
Okay, thank you, Mr. Eric, for all the nice historical stories. I would like to, I don't know, ask for your opinion, because like you said, it was a divorce between statistics and astronomy, then a remarriage, because is it because people's astrophysicists especially learn or realize that they don't know a lot of stuff, then they want to remarriage, and then maybe there will be a divorce again in the future? How would you see this again? Because yeah, that's what I see. Because it was interesting, it was started like astrophysicists, astronomers is a statistician, then divorce, then marriage again. Would there be a cycle, or yeah? But
Not
thank you
so
very much for
simple.
the good introduction.
Because a marriage and a divorce is one person and one person, and it's just one person. We are entire communities of people. So I'll just give you an anecdote, Arifin. When I was young and just beginning to be an astrostatistician, I would occasionally meet an older, very distinguished astrophysicist. And I would say, oh, I'm spending time talking to statisticians. They thought I was wasting my time. And one of them even said, I learned the least statistics I need for my problems. I'm anti-intellectual. I'm not interested in the methodology. I'm a physicist. The individual who told me that recently won the Nobel Prize in astrophysics. Okay, so this is what the leadership was doing. The leadership in America, at least, were astrophysicists. And they really didn't give a darn about the statistical methods. And it was younger X-ray astronomers and radio astronomers and just some other people who were not so prestigious and not very famous. And we're the ones who tended to speak to the statisticians. And so it was sort of was a rebellion, but it's really not. And I don't think there's going to be a divorce anymore, Arifin. And the reason is the big surveys. Now they have the CCD is as big as a table. It sees billions and billions of objects. And nobody can look at billions of objects and understand them without statistics. So we need machine learning, we need classification, we need statistics, we need tools for dealing with massive data sets and algorithms and codes as well. And that's why, insofar as survey astronomy is going to be important, which I think is the whole century, it's not the only thing we do, but it's certainly become the most popular thing. If you are in America and you are a government agency, you have $1 billion, you spend it on LSST. In Europe, you have €1 billion, you spend it on Euclid. It's a satellite they're going to launch soon. And these are survey instruments producing huge data sets that need statistics. This will not disappear.
Thank you very much. So yeah, thank you. I think because lots of data, there will be a total remarriage and it will be ever long-term and happy marriage. Yeah.
What I don't think only big data needs statistics. I think small data needs statistics too. So I actually think it's actually an interesting, intellectually interesting field. Most people don't agree with me. I'm the only one who likes to read statistics among the astronomers, but not the only one, but it's rare. But I think it is interesting. I don't think it's a minor topic of just boring mechanical use.
Thank you very much.
Okay, thank you, Arifin. Next, Bu Kiki Firdayanti, please.
Thank you, Pak Iqbal. Can you hear my voice?
Yes, I can. Hello, nice to see you.
Hello, Eric. first of all, I want to say that I've been wanting to attend your statistic course since I was students. So I'm happy now to hear your lecture. So I have two questions, but I'm going to ask as lecturer actually, because I wonder if you have some recommendation about when is the right time to teach astrostatistics to undergraduate students, because obviously they should learn the astronomy problem first. They should understand the problem in astronomy, what happened in astronomy, and then they can learn the tools to understand it. So is it the later stage of undergraduate level would be more beneficial to learn astrostatistics instead of in the early stage of undergraduate level? And the second question, oh, sorry.
Yeah, I think that's right.
Like
I teach this textbook to first and beginning graduate students, but a few undergrads come in to the class and they do not do poorly. They can test this. The mathematics in this is not as hard as quantum mechanics. Okay. They're already learning quantum mechanics. They can learn this. So as you say, they just need to know something about stars and galaxies and planets, understand the questions, but they don't need to know a great deal of astronomy or astrophysics. So I think advanced undergraduates and graduates, and we're now beginning, my colleague is now beginning to teach this course to advanced undergraduates only for the same reason. So I think that's right, advanced undergraduate.
I see. Can I ask the second question? So you mentioned that we have to learn a great deal of statistics to do astronomy properly, but as you know that learn takes time. So for students, probably it's overwhelming that they should learn many things first and then they can do proper statistics. Do you have any recipe for what is the basic knowledge that they should learn about astrostatistics to do well?
It is truly a difficult problem, Kiki. It is no absolutely trivial way of saying, you know, for one question in astronomy, you can find an easy answer, perhaps. But for all of astronomy, forget it. It's just too big. I don't mean
depend on the subject.
Two books. There's this book and Ivicic book, which has the same chapter headings. We didn't know this, but we cover much the same material from different perspectives. And mine's more classical inference, and theirs is more machine learning. But these books are not easy, a textbook. But I think the textbook should be at your institute, available. And maybe you don't read the whole textbook. Maybe you read just chapter 8 because you need to do regression now. Or maybe you use multivariate classification, you read chapter 11 or something like this. So having Ivicic and Feigelson textbook is a good start.
Okay, thank you, Eric. Thank
Available
you so
to
much.
you. Yeah.
Thank you, Pak Iqbal.
Thank you. Yes, thank you, Kiki. Next, CG, please.
Hello, good morning, Professor. Can you hear me?
Good morning. I can hear you indeed.
Or good evening. My question is on the first part of your talk. So you mentioned that Fisher said something like you should let the data speak for themselves. And the first thing that I thought of was cosmology, in particular the Planck CMB results. So because so I'm not sure about the accuracy of my statements, but as far as I know, they're analyzing the CMB, assuming the lambda CDM model. So they're assuming a model. So that's not letting the data speak for themselves, right? So I guess my question is
that's a funny example because some statisticians, American statisticians, actually won a statistics prize for doing a non-parametric analysis of it. You know, up and down the peaks like this, and they did non-parametrically, and the work was completely ignored by the astronomers. Because they are just completely convinced lambda CDM is correct, because the clustering agrees, and the weak lensing agrees, and the CMB agrees, and everything agrees. It got 3 Nobel Prizes or something, and everyone's so happy with cosmology today that they don't feel they need to do non-parametrics anymore. But it's an amusing story because the Carnegie Mellon statisticians got a prize for it.
Is it possible that okay, so I think I'm not sure, but I've read that there are certain observables in cosmology that you just have to assume some sort of model to understand. And so I guess my question is, can you still falsify a model with observational data, given that you're analyzing that same data with that model?
Oh, that's an interesting question. Right. The problem with the CMB is there's only one data set. Now, let's say you have a problem in galaxy clustering. So you go look over there and you make some inferences. And then what they do is they pay some astronomers to go look over there and to check it out. So they do it a different sample, just like they do in social science, to confirm or to not confirm. But with one data set, I agree with you. It's not so obvious. I don't have an answer.
Thank you, Professor.
Okay, thank you, Seiji. Next, Rafi, please.
Yeah, am I audible? Yes. Sorry
Yes,
that
yeah.
I don't have a webcam with my desktop. Yes.
It's okay.
So my question is that you mentioned that the papers of different statistical approaches are increasing with time, with years. But you also mentioned that the modelings are like, they don't know actually what modeling they're using to feed their data and doing the right statistical approach. So what is your comment on that? Yeah.
I can only make a personal comment. In my personal experience, mostly as editor for the last 5 years, is a wide range of quality. There are some beautiful modeling studies using the most sophisticated hierarchical Bayesian models with advanced algorithms, solving difficult problems with confidence that look beautiful. And then there are other people who take data, ask vague questions, use some procedure that may or may not be reliable, and they come up with an answer that of unknown reliability. And I see everything from lousy to excellent. So I don't think there's one thing going on. I think we are in transition, historical transition from the 20th century, when we really just, to use an American expression, we dropped the ball. We did not keep up with good methodology for 50 years. But now we are doing exciting things, but not uniformly. It's not everyone is excellent. So, but it's improving. And one way it's improving is your generation is paying attention. My generation, when I was your age, we would never go to a statistics workshop. There wouldn't be one to go to either.
Thank you so much.
Let me spend the next 5 minutes and finish my lecture. It is not very profound. Okay, this is a few slides on R. So, history of statistical computing, a subfield of statistics. Okay, when the first mainframe computers from IBM came along, statisticians would write papers, but they would not write code, and they allowed companies, corporations to do it. The big one was called SAS. An entire city of statisticians wrote the code, and here's some others. In 1980, a statistical expert in statistical computing named John Chambers worked at what we now call, what was going to call Bell Labs in New Jersey, And he was in Bell Labs, his friends developed a language called C. So he decided to write a statistics package similar to this that implemented mathematical statistics in C, and he called it S. Today you can buy it. It's called S+. 10 years later, the internet was becoming important, and two other professors of statistical computing, in this case in New Zealand, they decided to write an open source statistics package that the community could add to in a public way, so that it was not private to a company. So they decided to take S and they rewrote it and they called it R. And that's why it's called R. C to S to R. They made a team called the R Core Development Team, still exists, about 20 experts. And they made a GNU GPL public release. They set up a fashion for people submitting code that fulfills certain rules of quality. To their amazement, they called it CRAN or CRAN, Comprehensive R Analysis Network, CRAN. They couldn't believe it. It grew exponentially. This is log number of CRAN packages, linear time from 2001 to 2010, and it's now curving off of the line. It's a little less than exponential. Now, I looked last week or a couple of weeks ago when I gave Lucky these slides. There were 17,911 packages contributed by the community. Some are small, some are huge. But there's 5 new packages a day. We don't even know what they are. Nobody has an index of what's in it. My personal guess is 150,000 statistical operations, some of them very complex machine learning, some of them very simple, like median or mean. It is huge and constantly growing. It has everything in it, if you can find it. That's the problem. This slide is saying that R has become extremely important in American business called data science, data scientists, data miners. R is the most popular language. There's SAS, used to be the big one. Now it's R. There's Weka, early machine learning language. And there's others as well. Here is R winning out in the jobs. In 2013, there are more jobs to learn R than to use one of the older languages. And here's one about R has more questions and answers in Stack Overflow and cross-validated. These are programming advice blogs. Every question you have about programming in R, there is already been answered. So what is R? Well, it integrates data manipulation and data reduction. All of data reduction is a language. It has good graphics. But the most powerful reason for using R instead of Python or some other language is statistical analysis. It has much more and more advanced, more options. It has uniform documentation and coding, but the quality control for the packages is not good. I mean, nobody controls. They could have a bug. They do have bugs. All code is bugs. But AstroPy is very similar. Community contributed astronomy codes in Python. It can have bugs too. So in fact, the standards are probably higher than for Python. Okay, I don't know, it depends. No, I shouldn't say that. They're pretty high, but it's not guaranteed. It's fully programmable language. It looks like something called IDL in MATLAB, and it's free. You just download it as an app in 1 minute from this website, wwr-project.org, for these operating systems. The CRAN packages, you just do it on the fly. You just grab it in when you need it, and bingo, it's there. One line. It is because it's public domain, it allows you to bring in two-way communication with C and Fortran and C++, which are machine learning fast. Sorry, they're faster than Python and R. It's about the same speed as Python, maybe slower in some things and faster in others. It's about the same kind of compiler as Python. But neither of them are as fast as these three languages. And there's many thousands. It's the most largest, most widely used statistical software system. Nobody knows, at least 2 million people are using it, probably more, nobody knows. There's no company. There's enormous amount of resources. There's help files for base R, but there's hundreds of thousands of pages for the CRAN packages. Nobody knows. There's these lists that tell you a little bit about the CRAN, some of the CRAN packages. Vignette files are like articles about them. They're not always there, but they're often there. RStudio is a computing development environment that's very popular. It's run by a company. There are 1,200 blogs on R, and they're all collected here. Again, you can seek advice and little tutorials and lessons. Stack Overflow has 500,000 questions, 500 books, 2 journals. It's very big. Okay. So the hard part is not writing the script. We have entire PhD thesis written at Penn State, 200 or 300 lines. That's not the hard part. There's no coding to be done hardly. The hard part is knowing what you want, to learn, to think, consult, to check things. Finding what you want is easy. Understanding, then checking and confirming. You spend most of your time thinking, and you don't spend most of your time writing scripts because the code is there, usually. And that is my last slide. So I'm sorry I'm a little late, but thank you very much. I'll see you tomorrow.
Okay, thank you very much, Eric. Let's give applause to Eric.
Thank you.
Thank you. One more question, Eric. Can we share your slides that you already submit to Google Drive to the participants?
I sent you those slides, and you may share them with your community. Okay. Yes.
Okay, thank you very much. And yeah, we will give the link to all the participants. Okay, thank you very much, Eric. And let's end this session.